Today we will discuss Karnaugh maps. Karnaugh maps are a visual way to simplify Boolean expressions. They organize truth values of a function into a grid, making it easier to find and eliminate redundancies. Now we will discuss different examples of this Karnaugh maps and Karnaugh three variable K map. K stands for Karnaugh, so we will use the short form of Karnaugh map here as a K map. So a three variable K maps has 8 cells. And how we calculate these 8 cells? 2 10 raised to power 3, which is equal to 8. If 2 10 raised to power 8, if there are 4 variables, then there will be the 16 cells. How? 2 10 raised to power 4, which is equal to 3, and so on. These cells are arranged based on the binary value of variables. Let us see how this map works. Here are 3 variables, so we will take the A on our left side and B and C on our top side. So where we will distribute the values of binary values, it's A 0 1 and B 0 0. Here first 0 is represent B and the second 0 represents C, and so on. 0 1 mean BC, BC, and so on. So when A will 0 here and then BC are also 0, this binary value represent the decimal value of 0. And next cell is when A is 0, B is also 0, but C is 1. And here its binary value is, its decimal value is 1. In our next cell, A is 0, B is 1, and C is 1, which is equal to 3. In the next cell, and same, 0 stands for A, B, and C, 0 1 0 2, and so on. These cells also represent the same thing. And here is the best example of 3 variable K maps. And now we'll move on to the next one, and which is a 4 variable K map. This 4 variable K map, which I have already told you, which is equal to 2 10 raised to power 4, which is equal to 16, means for 4 variables we require the 16 cells. So here arrangements are AB on right side and CD on top side. So their binary value will distribute here 0 0 0 1 1 1 and 1 0. And CD 0 0 1 and 1 1 and 1 0. So again we will multiply AB CD. Sorry, it's an addition, not a multiplication. 0 0 0 0 AB, and it's C and D. Binary value is, decimal value is 1. Again AB CD, AB 0 0, CD 0 1. Its decimal value is 1. And here AB 0 0 and CD 1 1. Decimal value equal to 3. And at next cell, same repetition of these values will move on. And here is the 4 variable K map. Okay, now we will to the next topic, which is design combinational circuits. There are multiple ways to design such kind of circuits, but we will use here is multiplexer. Designing a 2-to-1 multiplexer MUX, which is the part of this combinational circuit. So first we will see what is multiplexer. A multiplexer is a common combinational circuit that selects one of several inputs signals and forwards the selected input to a signal output line. What do you mean by that? Let's discuss it here. Like here, inputs IO. When input 0 will represent it IO, and when input is equal to 1 will represent it I1. Controls SSS, which is selected inputs, which I have already told in the definitions. We select one of a several inputs signals and forward the selected inputs to the signal output, and here output is mine. So S, here is a truth table, S, I0, I1, and then output. S is selected. S, whenever S is equal to 0, whenever this S is equal to 0, we will select I naught. It means when S is equal to 0, I naught value will pass through this Y. Okay, when S is equal to 1, then I1 value will pass through this output. I hope so you get my point. Let me explain it again here. When I is equal to 0 means S, this value will pass through here. When I is equal to 0, here will be also 0. When I naught is equal to 1, 1 will pass through 1. When I is equal to naught, then 1 value will pass through here. Now in this case, if S is equal to I1, so I1 value will pass through here. S is equal to, in this case S is equal to 1, so mean I1 value will pass through this Y here. One value will pass through here, and etc. I think you get my point. I'll move on to the next slide, which is simple expressions, which I have already told you. When S is equal to 0, output will I naught, and when S is equal to 1, output is equal to I1. And here is an expression. Now here is a circuit diagram. This diagram represent that S, whenever S starts from this and move it here like an arrows, if we follow the arrows we will move towards our output. So now we will conversion of AND or NOT circuits into circuit using only NAND or NOT gates. Here is a conversion like AB, here in NAND gate and then AND gate. This circuit represent when A is equal to 0, B is equal to 0, then NAND A is equal to 1, AND is 0. When B is 1, NAND is 1, but AND is 0. Here is move on to the AND to NAND conversion. In the same way, we will convert a NAND gate AND gate like here I have shown in a truth table. This here, whenever A is equal to 0, B, it stands for whenever A is 0 or B is 1, NAND will be 1, because if one value is true, NAND gate will true. If here is a conversion of NOT gate. Truth table A stands for 0 1, and NOT mean opposite of input. If input is on, then output will off. If input is off, then output will on. This is all from